motorcycle has to move with a constant speed on an overbridge, which is in the form of a circular arc of radius r and has a total length L. Suppose the motorcycle starts from the highest point. What can be its maximum velocity be for which the contact with the ground is not broken at the highest point? And the next one is, if the motorcycle goes at a speed 1 by root 2 times the maximum speed found in the part A, where will it lose the contact with the road? And the last part, what maximum uniform speed can it maintain on the bridge if it does not lose contact anywhere on the bridge? So if we are considering this kind of a problem, so if we understand this arrangement, so this is the overbridge the question is talking about, and it is moving in a circle of radius r, or the arc of radius r, and the total length is equal to L, which is the length of the overbridge. Now at the highest point, so at the highest point somewhere here, when the motorcycle is here, so if it is moving with a speed v, then it will be exerting a force mv square by r in this direction, that is away from the circle, and the weight mg is going to act in the downward direction. So if we wish to calculate for the contact not broken, so if the contact is not broken, then I can say the normal reaction just becomes 0, or I can say that mv square by r is balanced by mg, and from here we obtain v is equal to root over rg. So this is going to be my answer for the first part. Now in the next part it is saying, if the motorcycle goes at a speed of 1 by root 2 times the maximum found in the part A, where will it lose the contact with the road? So if we are considering this portion over here, so now we say that the question is giving us a velocity of equal to 1 by root 2 times of the previous velocity, that is root over rg. And if we consider that it lose at a point somewhere here, if we consider that it loses contact, suppose somewhere here, which I am referring as a point T, you can refer it in any which way, A, B, C, D. So if we consider this, so I say that the weight is acting in the downward direction, that is mg, and if this angle is theta, then this angle is also theta, that is alternate angle, and the weight component which will act over here will become mg cos theta. So mg cos theta is balancing mv square by r at this instant, that is at a point t. So I can write it in this way, that when it is at a point t, so it will be losing the contact only if the weight component, that is mg cos theta, becomes equal to mv square by r. So from here we can say that v square is equal to rg by 2, and if we put it here, so we get it as mg cos theta is equal to m v square by r. So we get the value of cos theta as half, that is theta equal to 60 degree. So at an angle of 60 degree it will lose the contact, or I can say that the distance which it is going to travel from the highest point, if we wish to calculate the distance it travel from the highest point, then this angle is 60 degree and this radius is r. So 60 degree can be written as pi r by 3. So this arc length, which I call it as delta L, can be written as pi r by 3 from the highest point. So on covering a distance of pi r by 3 from the highest point, it will lose contact over there. Now in the last part it is asking, what maximum uniform speed can it maintain on the bridge if it does not lose contact anywhere on the bridge? So the maximum value of angle which is possible in this particular problem can be ascertained like this, that if this is the length of the overbridge L and it is moving in a circle of radius r, so at this point it is subtending the maximum value of the cos. So if I call this as alpha, so for this point we can write it as that the weight mg is acting in this direction. A weight component which is equal to mg cos alpha will act here, and it must balance mv square by r. There is also weight component mg sin alpha, but this is of no use to us in the present context. So the chance of losing contact is maximum at the end of the bridge. So at the end of the bridge, I can say that alpha is equal to L by 2r. That is arc length upon radius. So the arc length is L by 2 and the radius is r. So alpha is equal to L by 2r. So we can say that for this portion it is important that mv square by r is equal to mg cos of alpha. So from here I can write that v is equal to rg cos of L by 2r square root. So this is the answer for the third part.